Okay, number one, find the absolute local maximum minimum values of f of x equals x squared minus 2x plus 3 on the interval from -4 to 2 with equals 2, which means that the points themselves are included. That might come into play and be important. First thing, I could graph it, but if we just consider this number -4, if I put that in, I'm going to get 16 plus 8 is 24 plus 3 is 27. Kind of a large number, so I might have to scale the graph a little bit. So rather than just graphing it right off the bat, let me get some critical numbers so I can at least figure out kind of the limits of this thing, highest and lowest points that I'm going to get, so I can kind of get a feel for where I need to put the points. I do want to graph those since it's asked for local maximum minimum values. I do want to graph it so I can kind of pick those out. So if I consider f prime of x, it's going to be 2x minus 2. The three criteria are, for critical numbers, we need the derivative equals 0, the derivative is undefined, or endpoints. Starting off with the equals 0 part, 2x equals 2, so x equals 1. So my critical numbers, put C for critical, are 1. 2x minus 2 is not undefined ever, so no critical numbers come off of that. And -4 and 2 are my endpoints, so those are critical numbers. So those would be the three numbers I'd really want to get the x values for to really help me graph this thing. So x, y. I put -4, 1, and 2 in. And again, if I put -4 in, I'm going to get positive 16, plus 8 is 24, plus 3 is 27. If I put 1 in, I'm going to get 1 minus 2 is -1, plus 3 is 2. If I put 2 in, I'm going to get 4 minus 4 is 0, plus 3 is 3. So it looks like if I go with a 3 scale here, we might be sufficient to be able to get this on here. I'm going to put x to 1 scale. 1, 2, 3, 4, 3, 6, 9, 12, 15, 18, 21, 24, 27. 1, 2 would be about here, and 2, 3, of course, would be about here. I want to pick a couple extra points just to fill in the rest of the values. -3, -2, -1, and 0. 0 minus 0 plus 3 is 3. 1 plus 2 is 3, plus 3 is 6. 4 plus 8, 4 is 8, plus 3 is 11. 9 plus 6 is 15, plus 3 is 18. So 0, 3, -1, 6, -2, 11, and -3, 18. So it creates that picture there. And just looking at it, a critical number happened here, and here, and here. If I were to connect those dots, we can see that this critical number represents the lowest point, this represents the highest point in the graph, and this represents the highest point in its area. So if I'm identifying absolute and local maximum and minimum values, I'm going to have an absolute minimum of 2 at x equals 1, an absolute maximum of 27 at x equals -4, and a local maximum of 3 at x equals 2. Again, no local minimum. This is an absolute minimum, but there's no local minimum. And looking at increase and decreasing also, the graph's decreasing all the way to here, then it increases, so it switches from decrease to increase minimum. It's increasing to hit till its endpoint, so that shows me it's a maximum. Just make sure you identify those properly. If either of these here or here have been an open circle because these didn't say equals, like for example, if it just said -4 less than x, now we have an open circle. Now there's no absolute maximum because there's no point there to identify. I'm not sure I'd do that to you, but just be cautious of that. Number 2, find the absolute local maximum minimum values of this. A piecewise function, the best way to do it is just to graph it. And keep in mind with piecewise functions that we go from an endpoint to an endpoint, so there's no arrows to be seen. So if I look at the top one I did in blue, I want to start at my endpoint, end at my endpoint, so I'm going to go from 0 and 1 to 1. I'll maybe pick a number in between, 0.5 is between. And I might just evaluate the function 3 minus 3x. If x is 0, 3 minus 0 is 3, 0.5. 0.5 times 3 is 1.5, 3 minus 1.5 is 1.5. 3 times 1 is 3, 3 minus 3 is 0. And then the second part of the graph is 2x, starting at 1, ending at 3. I'm going to pick 2 in between. Notice that it says 1 is less than x, so this is going to be open circle point. Everything else, rand points, equals, equals, equals. So this is a closed circle, this is a closed circle, and this is a closed circle. So the endpoints are what you have to concern yourself with. The points in between, they're always closed, but the endpoints themselves can either be open or closed depending on the inequality. For the numbers between 1 and 3, you're supposed to double 2 times x, so 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. So if I get my 3 points, 0, 3, 1, 2, 3, 4, yeah, they all fit. So 0, 3, closed, 0.5, 1.5, closed, 1, 0, closed. And again, endpoint to endpoint, we just connect those dots with a straight line. Then the black ones, we got 1, 2, open, 2, 4, closed, and 3, 6, closed. Goes like so. So looking at that graph, the blue and the black, the absolutely highest point on the graph, so absolute maximum, is this point here. So it's absolute maximum of 6 at x equals 3. The absolutely smallest point is this one here, so absolute minimum is going to be 0 at x equals 1. This is the highest point in its general area, so the graph, if I'm just going along here, high going down, so that's a local maximum of 3 at x equals 0. Okay. This has already been identified as the absolute maximum, absolute or minimum maximum. This point would be a local minimum for that area, but it's an open circle. So again, open circles don't count. So there's my absolute, there's my local, and that's everything I needed to find out about that one. For number 3, if they give us an interval and ask for the absolute minimum max, then we're simply going to find the critical numbers, evaluate, and then determine which one's the biggest and smallest. They don't care about locals in this situation. So basically the technique here is, number 1, find the derivative. So f prime of x, it's a rational function, so I'm going to do low d high minus high d low over the square of what's below. Then I simply evaluate or simplify as much as possible. 6x squared minus 12x squared makes negative 6x squared. 3 times 1 is plus 3, all over 2x squared plus 1, the quantity squared. That's as simple as I can get the first derivative. And as far as critical numbers concerned, we want criteria 1. We want the top to equal 0. We want the fraction equals 0. If the top equals 0, we have 0 divided by number. So if I do negative 6x squared plus 3 is equal to 0, that gives me 3 equals 6x squared, which means 1/2 is equal to x squared, which means x is going to equal plus or minus the square root of 1/2. So plus or minus 0.71, if you will. Criteria 2, we want the bottom to equal 0 because the criteria 2 is the derivative is undefined. 2x squared plus 1 can't equal 0, so there are no criteria 2 numbers. Criteria 3, we're looking for endpoints, which are 0 and 2. Okay. Endpoints also establish a region that we care about, so if we get critical numbers not within the endpoints, we throw them out. So where I've got the plus or minus 0.71, I'm going to throw the minus 0.71 out because it's not between 0 and 2. So my only critical numbers here are going to be 0, 0.71, and 2. So what I want to establish here now is minimum, maximum values. I've got 3 critical numbers, so I simply have to evaluate f of 0, f of 0.71, and f of 2. And whichever the biggest number is the maximum, the smallest number is the minimum. So if I clear that out, type in my function 3x divided by, it's more than one thing on the bottom, so parentheses for the bottom, 2x squared plus 1. And I enter my 3 numbers that we got, my critical numbers are 0, 0.71, and 2. And we get 0, 0, 0.71, 1.0607, and 2 is 0.67. So, looking at my 3 results here, 0 is the smallest, 1.0607 is the biggest. That's in the middle, so that would be local minimum probably, but we don't care about locals, we're just looking for absolute. So absolute minimum of 0 at x equals 0, absolute maximum of 1.06 at x equals 0.71. That's all they're asking for, number 3. That's all I need to do, so I'm going to move on to number 4. Same question, absolute maximum minimums. Once again, the job is to find our critical numbers. And it does give us an interval again, 0 to 2 pi. So only numbers between 0 and 2 pi even matter. So when I do criteria 1, I might think about that while I'm doing that. So f prime of x is going to be 1 minus 2 sine of x. Okay, so for criteria 1, criteria 2, and criteria 3, we already know x equals 0 and 2 pi. This is never undefined, so criteria 2 is the empty set. As far as criteria 1 is concerned, if I set it equal to 0, I'm going to get 1 equals 2 sine of x. So sine of x equals a half. So sine of x equals a half, so x is going to equal any number between 0 and 2 pi, where sine is equal to a half. So x is going to equal pi over 6, and again at 5 pi over 6. And these are exact numbers you have on your formula sheet, so I'd expect exact answers for these, since we have the ability to do that. So I got 4 critical numbers altogether, so again, I have to evaluate every one. So f of 0 equals something, f of pi over 6 equals something, f of 5 pi over 6 equals something, and f of 2 pi equals something. Again, my calculator can evaluate that stuff for me. The original function, again, when I'm evaluating these, I'm evaluating the function x plus 2 cosine of x. All the other stuff is there. I'm going to go to my mode to make sure I'm in radians, not degrees. Always, anytime you can do sine, cosine, tangent, make sure you're in radians, not degrees when we're in calculus. If you're in physics, you probably want to be in degrees, not radians. I want to delete all the stuff in there and just type in my number. So it's 0, type in pi divided by 6. It estimates it for you, but you're putting in exactly 5 pi over 6 and 2 pi. And we end up with 0 to 0.5236 is 2.26. 5 pi over 6 is 0.89. And 6.28 is 8.28. Alright, and just like that, we get 4 results. Again, the smallest one's the absolute minimum, the biggest one's the absolute maximum, the other 2 don't matter. So, absolute minimum of 0.89 at x equals 5 pi over 6. Absolute maximum of 8.28 at x equals 2 pi. Go ahead and round the results, but give me the exact answers for the critical numbers on this one, because again, we have the ability to find those. If it said sine of x equals like a third or something that's not on your sheet, then of course just inverse sine it, give me those answers. I think I'll probably stick to the sheet though, just to make sure we get all the proper answers. Number 5, I want to find intervals of increase, decrease, maximum, minimum values, and intervals of concavity inflection points. So we're required to use the first and second derivatives. First derivative tells me the answers to these. The second derivative gives me this information. So if we start off with those derivatives, f prime of x is simply going to be 6x squared plus 12x minus 18. F double prime of x is going to be 12x plus 12. So as far as A and B are concerned, intervals of increase, decrease, and max and minimum values, I'm going to work with my first derivative. I want to find critical numbers, criteria 1, 2, and 3. Criteria 1 is the derivative equals 0. We have a quadratic function. If we set that equal to 0, just use a quadratic formula. Type in my A, B, and C, which are 6, 12, and 18, or 6, 12, and negative 18. We get zeros of 1 and negative 3. Criteria 2, undefined derivative, doesn't happen. Criteria 3, endpoints, I don't see any. So we get 2 critical numbers, 1 and negative 3. As far as question A is concerned, we start at negative infinity, go to the smallest critical number, the smallest to the next biggest, and so on. Once we run out of critical numbers, we go up to infinity. We pick test points on each interval, -4, 0, and 2 will do fine. And we're evaluating this function here for these numbers. -4, it's probably easy enough just to go with y equals and type in that since the numbers are rather large. So 6x squared plus 12x minus 18. And if I just type in -4, 0, and 2, we get positive, negative, positive. So that tells me it increases, it decreases, then it increases. So there's part A, intervals of increase, decrease. Increasing on these, decreasing on that. Increase, decrease hits a maximum. Decrease, increase hits a minimum. So for question B, find the local max and minimum values. We can say local max of something at x equals -3, a local min of something at x equals 1. To get those actual values, we go back to the function f of x, type in 2x cubed plus 6x squared minus 18x, and we have -3 and 1. So -3, 54, 1, -10. Just like that, we've answered questions A and B. So question A, increase and decrease. Question B, local min and local max. All right, as far as question C is concerned. Question C, it wants intervals of concavity and inflection points. So now we've got to focus on the second derivative. F double prime is 12x plus 12. So again, the three criteria for critical numbers. Criteria 3, no endpoints. Criteria 2, undefined, not going to happen. Criteria 1, set that equal to 0, so 12x equals -12, so x equals -1. So critical number is -1, that's the only one we get. So -infinity to -1, and then from -1 to infinity. We're testing these intervals, so -2 and 0 will do fine. We're testing f double prime, so we want to evaluate this function for these numbers. -24 plus 12 is negative. 0 plus 12 is positive. So it's concave down, it's concave up. So there's my intervals of concavity. As far as inflection points are concerned, when concavity switches at a number that's going to create a solution, there's an inflection point. So there's an inflection point of -1 comma something. To get to something, we're just evaluating the same function f of x at our critical number. So if we put -1 there, we get a value of 22. So as far as the test is concerned, when you're doing this task number 5, you should get some polynomial function, and you're going to give me information of that variety. I want increasing, decreasing intervals. I want min and max values and where they occur. I want to know concavity up and down, and I want to know any inflection points that occur, and that's what we're looking for. Number 6, same problem, different function. So this time we have a rational or a radical function. I'm going to shrink this down a little bit just so there's more room to write. F of x equals that. So intervals of increase, decrease, and max and minimum values are again first derivative information. And the intervals of concavity inflection points are second derivative information. So first thing I want to do is find derivatives. And what I recommended doing was getting those derivatives simplified. So f prime of x equals something. F double prime of x equals something. For this specifically, I'm going to do my work here and I'm just going to erase it when I get the answers. This is the structure you should expect in number 6, and this is kind of what I want you to do for this problem. First off, I'm rewriting f of x in a better form for differentiation. Like so. Making a power function instead of a radical function. It's a product, so I'm going to do the product rule. So f prime of x is going to equal 1d2. d2 is a chain rule, so 1/2 times x squared plus 4 to the -half times 2x. Plus 2d1 is going to be x squared plus 4 to the half times 3. Okay, that's the derivative, and there's nothing wrong with that derivative, but it's hard to differentiate that. We need to get a second derivative. So what I want to get across to you here is if we make f prime as simple as possible, f double prime is easier to do. So first off, this 2 cancels that 2. Will that happen? Maybe, maybe not. But just keep in mind that if things cancel, go ahead. When I'm looking at all this stuff, 3x squared is all on top, and I got a square root of x squared plus 4 on the bottom. That's being added to the second term, which is just 3 times the square root of x squared plus 4. And that's exactly right. That's the first derivative. But again, is that easy to differentiate? I got to do quotient rule with a radical involved, and I have to do a chain rule going on over here. So maybe the second derivative is a little hard to complicated here. So here's what you can do on this problem. And again, it's going to have this structure, so this same thing will happen on the quiz when you do it. If I make this fraction have that denominator, so just multiply top and bottom by the square root of x squared plus 4, what happens is you get one fraction with the square root of x squared plus 4 on the bottom. And then, of course, this first fraction already has x squared plus 4 and the square root of x squared plus 4, so nothing happens to the numerator. The second fraction, though, notice this times this just makes x squared plus 4 with no radical. So we're multiplying a radical times itself. We're going to end up with a non-radical on top, which makes our first derivative simplified as much as possible down to 6x squared plus 12 over x squared plus 4 inside a square root. This is a much more concise, easier to deal with derivative than this is. And again, you should expect that same stuff to happen on the test that you take. So 6x squared plus 12 on top, the square root of x squared plus 4 on the bottom. And again, this is scratch paper work over here, so I'm going to just erase all this stuff. So now if I'm trying to do the second derivative, I want to start there. And again, rather than starting actually right there, I'm differentiating. So rather than have a radical structure here, I would rather have a half power structure. So I'm going to put that over x squared plus 4 to the half. So now if I differentiate second derivative f double prime, I'm going to get low d high, which is going to be x squared plus 4 to the half times 12x, minus high d low, 6x squared plus 12, times 1/2 times x squared plus 4 to the negative half, times 2x. Over the square of what's below, that's just going to be x squared plus 4 to the first. And again, the same structure for the test. You should expect some of the same stuff to be happening here. If I simplify this, if I beautify it up a little bit and make it as pretty as I can possibly make it, it looks like this. F double prime of x equals, this is going to be 12 times the square root of x squared plus 4. This 2 cancels that 2. Top, top, bottom. So I'm going to get minus a fraction, 6x cubed plus 12x all over the square root of x squared plus 4 all over x squared plus 4. Okay, so what I want you to see when you're looking at this and you're preparing for this test, you should expect to get something along those lines. Term 1, term 2, term 3. And one of the terms, probably term 2, is going to be some fraction inside of a fraction. It's not good math to leave it like that. So I want to multiply this entire numerator by the square root of x squared plus 4. And the entire denominator also by that. But I would probably use this structure on the bottom since we're multiplying common bases. So if I do all that multiplication, what ends up happening, f double prime of x, is this times this is going to make 12 times x squared plus 4. Square root times square root makes it not a square root. This times this, the square roots of x squared plus 4 cancel, leaving with minus this numerator. Be careful, that numerator is more than one thing. It's being subtracted, so we're subtracting the entire thing. So minus this and minus that. All that goes over x squared plus 4 to the 3/2 power. And then what's left to do is to simplify as much as we possibly can. So, you know what, I left an x off of here. I saw that now. All right, 12x, still 12x, still 12x. Okay, so f double prime of x, if I finish simplifying it out, this makes 12x cubed plus 48x minus 6x cubed and minus 12x. And again, that's a very easily forgotten sign there. So minus that and minus that all over x squared plus 4 to the 3/2 power So if combined like terms, my best second derivative is going to be 6x cubed plus 36x all over x squared plus 4 to the 3/2 power. And again, all this work, scratch work, I would get some graph paper or something, a scratch sheet of paper to work with during the test. Do all this somewhere else, and then just come up with those two derivatives. I'll believe you did that. If you want to staple your scratch paper to your final quiz, that's fine with me. All right, so that gets me to this point. And now I got to find my critical numbers again. So, working with the first derivative, f prime of x, criteria 1, 2, and 3. And let's start with criteria 3. There are no endpoints. Done. Criteria 2. A rational structure is undefined when the denominator equals 0. X squared plus 4 will not equal 0, so therefore the square root of 0 is not going to occur, so there are no undefines. The only place we have to worry about is the top. 6x squared plus 12 also does not equal 0 ever. If we tried it out, 6x squared plus 12 equals 0. That means 6x squared equals negative 12. You can't make a negative number from a square, so it's not possible. So there's also no critical numbers for the first derivative. So altogether, all three criteria fail, so there's no critical numbers. So negative infinity to infinity is going to either always increase or always decrease. I'll pick a test point of 0. 0 plus 12 is 12. The square root of 4 is 2. 12 over 2 is 6, which is positive. It's always increasing. All right? Therefore, there are no max or min values. All right. Question C, intervals of concavity and inflection points. So we have 6x cubed plus 36x as our numerator. So again, we have criteria 1, 2, and 3. No endpoints. X squared plus 4 cannot equal 0. No undefines. 6x cubed plus 36x equals 0 gets me 6x times x squared plus 6 equals 0. 6x equals 0, x squared plus 6 equals 0. 6x equals 0 gets me x equals 0, x squared plus 6 equals 0 is not possible. So we get one critical number, 0, for the second derivative. So if I do from negative infinity to 0, and then from 0 to infinity, and I pick a test point, negative 1, positive 1, put negative 1 in place of this, negative 6 minus 36 is negative 42 over a positive number. 6 plus 36 is positive, 42 over a positive number. The bottom is always positive, x squared plus 4. So it's concave down and concave up. The concavity switches at 0, so there's an inflection point at 0 comma something. If I put 0 in place of x, 0 times the square root of 4 equals 0. So inflection point of 0, 0. Again, that's the basic structure. The difficulty of this problem is finding the derivatives. Find the derivatives correctly, you'll be in good shape. Again, if you get no critical numbers, there's simply one interval from negative infinity to infinity. It's always increasing, always decreasing. If there were no critical numbers here, it's either always going to be concave up or always concave down. So keep that in mind. Number 7, f of x equals square root of 3x minus 2 cosine of x from 0 to 2 pi. This time we have an interval. So every time we do critical numbers, 0 and 2 pi will be critical numbers, and all answers are going to be between 0 and 2 pi. Intervals on concavity or of increase and decrease come from our first derivative, and intervals of concavity come from our second derivative. So f prime of x equals something. That answers questions A and B. F double prime of x equals something. Be careful with square roots and don't freak out or make it seem like it's more difficult because there's a square root in it. Square root of 3 is a number, it's being multiplied by x. So when I do f prime of x, it's simply going to be the square root of 3. Just like if it said 5x, it'd be 5. 10x, 10. Dog x, dog. X is not underneath the radical, nothing weird's happening there. So square root of 3 is just a number being multiplied by x. Its derivative is just the square root of 3. Negative 2 cosine of x is plus 2 sine of x. Remember, the derivative of cosine is negative sine. Negative, negative makes a positive, and the 2 just comes along for the ride. So that's f prime of x. I can't make it any prettier than that. Moving on to f double prime. Okay. The derivative of the square root of 3 is 0. Again, so square root, that's the square root of a number. The square root of 17 is 0, the square root of negative 5 is 0, the derivative of the square root of 3 is 0. So derivative of number is 0, so that's irrelevant. Derivative of sine of x is cosine of x, so 2 cosine of x is the derivative of 2 sine of x. So there's my second derivative, simplified as much as possible. So just like that, I got my first and second derivatives. I'll stick to sine or cosine function in on the test, so just be comfortable with the derivatives of sine and cosine, it'll be fine. And again, my job is to find all the answers between 0 and 2 pi for each of these. So for critical numbers, for the first derivative, endpoints, of course, 0 and 2 pi. Sine and cosine are never undefined, so there's no criteria 2 happening. For criteria 1, I want the square root of 3 plus 2 sine of x to equal 0. That means that 2 sine of x equals negative the square root of 3. Divide by 2, divide by 2. So I want the sine of x equals negative square root of 3 over 2. That occurs at 4 pi over 3 and 5 pi over 3. And again, these numbers will be on the formula sheet you have, so if you didn't already memorize them like you were supposed to last year and keep them in your brain, you still have that formula sheet available to you. Make my 5 a little prettier. Alright, so just like that, I've got my critical numbers, and again, the only real work I had to do there was find where that equals 0. It's pretty easy to do. I've got 4 critical numbers. I'm starting not at negative infinity, positive infinity. I was going to start at 0 and at 2 pi. So from 0, notice that it's bracketed 0 because it says equals to. 0 to the smallest number. From that number to the next biggest number. And from that number to the next biggest number. And I'm bracketing 2 pi because it says equals 2 pi. So there's my intervals, starting at 0, ending at 2 pi, stopping along the way at 4 pi over 3 and 5 pi over 3, which are between 0 and 2 pi. And 4 pi over 3 is a little bit bigger than 4, so 1's between 0 and 4 pi over 3. A little bit bigger than 4, a little bit bigger than 5, so maybe 5. If you're not sure, what these equal, if you come over here and type in 4 pi over 3 and 5 pi over 3, get some decimal approximations, you can see very clearly 5 is between those two numbers. And of course 2 pi, there's 5 pi over 3, there's 2 pi, 6 is obviously between those two numbers. I like picking whole numbers when I pick these if I can, so I'm going to do that. What I'm testing is the derivative. The derivative is the square root of 3 plus 2 sine of x. So I'm going to y equals the square root of 3 plus 2 sine of x. Be careful with your calculators that you have a beginning parentheses, end parentheses. Square root of 3, that's it. Sine of 2x, or 2 sine of x, that's all we're doing there. I type in 1, 5, and 6. And I see positive, negative, positive. That means it increases on this interval, it decreases on this interval, it increases on this interval. So again, for question A, there's question A answered. Also, I know that it hits a maximum here and a minimum here. Okay. It says local maximum minimum values, which means that there's also a maximum minimum here also. So think about this. If you start somewhere and it increases, where you're starting is a minimum. And if it's increasing till you get to the end point, you're looking at a maximum. Right, so just again, for local maximums, minimums, if you have an end point there, you're going to have to imagine what the graph would look like around the end point. So I can see that we have a local min of something at x equals 0, a local max of something at x equals 4 pi over 3, another local minimum of something at x equals 5 pi over 3, and finally a local maximum of something at x equals 2 pi. I'm starting off calling them all local. We'll worry about what they actually are in a minute. So if I type in my function here, y equals, I'm going to type in the square root of 3, and again, type in the square root of 3, x. The square root of 3 is all we have the square root of. X is outside the radical, minus 2 cosine of x. Again, I'm already in radians. I already checked that earlier, but just to verify. My 4 critical numbers are 0, 4 pi over 3, 5 pi over 3, and finally 2 pi. my results are -2, positive 8.26, 8.07, and finally 8.88. Okay, once I did that, my critical numbers all represent the minimum maximum values of this function. That's the absolutely smallest, so I can actually change that to an absolute minimum. And this is absolutely biggest, so this is absolute maximum. I prefer to have absolute written there. I'm not going to count wrong if you say local, but just keep in mind there will be an absolute probably within an interval, so make sure that you identify those. Second derivative, 2 cosine of x. Again, 3 criteria, 1, 2, 3. Obviously, criteria 3, we're going from 0 to 2 pi. Cosine is never undefined. Cosine equals 0 at pi over 2 and again at 3 pi over 2. Both numbers being between 0 and 2 pi. Again, your sheet will tell you that. My intervals will be from 0 to pi over 2, from pi over 2 to 3 pi over 2, and then finally from 3 pi over 2 to 2 pi. Okay. So concavity, we're going to pick numbers, 1 is between those, 3 is between those, and let's go with 5 is between those. Cosine of anything between 0 and pi over 2 is positive, so positive times 2 is positive. Between pi over 2 and 3 pi over 2, cosine is negative. And then between 3 pi over 2 and 2 pi, cosine again is positive. Okay, concavity is down, concave up, concave down, concave up. So there's my concavity answers. There's an inflection point here and here. Okay, there is no inflection point at the end point. So where you have minimums, maximums, they hit high and low points. Inflection points don't occur at an end point just because they're there, so keep that in mind. So all I really have to do is figure out for inflection points are going to be pi over 2 comma something and 3 pi over 2 comma something. Again, I'm evaluating f of x, so I just type in pi over 2 and 3 pi over 2. I get 2.72 and 8.16. Just like that, I got all my concavity figured out, got my increase and decreasing intervals, got my minimums and maximums identified, I've got my concavity inflection points identified, everything I needed. Number 8, limit as x approaches negative infinity of all this stuff. First thing, if you're dealing with polynomial stuff, the first thing I would do is I would get everything simplified as much as possible. So limit as x approaches negative infinity of, the top is perfectly fine, 5x cubed minus 7x squared plus 2x minus 5. The bottom, I multiply x times all this stuff, I get 3x cubed plus 2x squared plus x. Multiply 4 times everything, I'm going to get plus 12x squared plus 8x plus 4. So altogether 3x cubed plus 14x squared plus 9x plus 4. Okay, so again, completely simplify the top and the bottom. And that might be scratch work somewhere out of the way. Then, you're looking at a rational structure. You want to get the highest power of x established in the entire problem, which is x cubed. 1 over x cubed is the magic thing that's going to help us get the answer. I'm going to do the entire top and the entire bottom times that. So I've still got limit. X is still approaching negative infinity. And if I multiply 1 over x cubed times all this, I'm going to get 5 minus 7 over x plus 2 over x squared minus 5 over x cubed over 3 plus 14 over x plus 9 over x squared plus 4 over x cubed. We're approaching negative infinity. Whether it's positive or negative infinity, if you take a number divided by an infinity, you're going to get 0. So, and if I worry about the sign of 0, this would be a positive 0, because negative infinity and negative make a positive. Negative infinity squared is positive. This is also a positive 0. Negative infinity cubes negative. Negative negative makes a positive. On the bottom, I got 3. 14 over negative infinity makes negative 0. 9 over negative infinity squared makes positive 0. Infinity cubed, negative infinity plus 4 makes minus 0. The only place signs really would help us here for the zeros would be if we're adding all, like this, obviously the top is positive, the bottom might be positive or negative. I'm not sure how much bigger this 0 is than these zeros and vice versa. So, but the whole point is we get a bunch of zeros. Added, subtracted. So the result of this limit is just 5/3. All right, so simplify as much as you can, multiply by 1 over the highest power. Only the numbers that don't have over x matter, and that's the result of that limit. Number 9, same deal, except in this case, if I put infinity in, I'm going to get infinity minus infinity, which I don't know what it equals. So what I want to do is I want to make this into a rational structure. I'm going to multiply top and bottom by the conjugate of this. Same two objects, different sign in the middle. Top and bottom of the fraction multiplied by the exact same thing. So we're going to get limit as x approaches infinity. Difference times sum of the same two objects gives me the first object squared minus the second object squared. All over the bottom, which is 1 times that, so just that. If I simplify the top as much as I possibly can, I'm going to end up with 9x squared minus 9x squared canceling, so 7x minus 3 on top, and the square root of 9x squared plus 7x minus 3 plus 3x in the bottom. And then it's just a matter of finding the highest power of x, x to the first, half and 0, and x to the first. So first power is the highest. Keep in mind inside the radical 2 over 2, 1 over 2, 0 over 2. So 1 over x on top, 1 over x on bottom, or the square root of 1 over x squared on the bottom. Take your pick. This times this one, this times that one. So limit as x approaches infinity. It's going to be 7 minus 3 over x over the square root of 9 plus 7 over x minus 3 over x squared. Multiplying the 1 over x squared inside the radical, 9, 7 over x, 3 over x squared. And then 3x times 1 over x makes plus 3. If I substitute infinity in now, anything over x is going to go to 0, so I'm going to get 7 minus 0 on top. I'm going to get the square root of 9 plus 0 minus 0 plus 3 on the bottom. Those zeros all go away. So I'm up with 7 over the square root of 9 plus 3. So 7/6 is the answer to that one. Finally, number 10, find the asymptotes of this. Use them together with concavity intervals, increase and decrease to sketch the curve. So, first of all, asymptotes. Vertical asymptote is all about the denominator. If the denominator equals 0, you get a vertical asymptote, so x equals 1. Horizontal asymptote is all about limit as x approaches infinity. So limit as x approaches infinity of this. X is the highest power, so multiply by 1 over x, we're going to get 2 minus 7 over x over 1 minus 1 over x. 2 minus 0 over 1 minus 0 gets me y equals 2. So x equals 1, y equals 2 are my asymptotes. Next thing, the first derivative. If I do low d high, I'm going to get x minus 1 times 2. If I do high d low, I'm going to get minus 2x minus 7 times 1 over the square of what's below x minus 1, the quantity squared. That gets me 2x minus 2 minus 2x plus 7 all over x minus 1, the quantity squared, which is 5 over x minus 1 squared. So f prime of x is 5 over x minus 1 squared. F double prime of x, if I change this to 5 times x minus 1 to the negative second power, f double prime of x is just a chain rule with power rule involved. So negative 10 times x minus 1 to the negative third times 1. So negative 10 on top over x minus 1 to the third on the bottom. Again, this would all be scratch work somewhere out of the way so it doesn't jumble up all your stuff. Critical numbers of the first derivative, criteria 1, 2, and 3. The top does not equal 0 ever. The bottom equals 0 and x equals 1. There's no endpoints. So the only critical number is 1. So I'm going to go from negative infinity to 1, and then from 1 to infinity. If I test the intervals, I'm going to go with 0 and let's go with 2. 0 squared is 0. Negative 1 squared is 1. 5 over 1 is positive. 1 squared is 1, 5 over 1 is positive, it's always increasing. Okay, now there is a stoppage at 1, so don't say it's increased from negative infinity to infinity, but it's increasing on both of these. So increasing, increasing. Usually if there's a swap, if it goes increase, decrease, we get a maximum or minimum if it goes from decrease to increase. But x equals 1 is an undefined location. There's an asymptote there, so there's actually no point at 1. So even if it went increase, decrease, or decrease, increase, there would not be a minimum or maximum value there. All right. As far as the second derivative is concerned, criteria 1, 2, and 3. No endpoints. Negative 10 doesn't equal 0, so this fraction can't equal 0. And again, at 1, we get an undefined. So, if I set up my intervals from negative infinity to 1 and 1 to infinity, test point of 0 and 2, 0 minus 1 is negative 1, cubed is negative 1, negative 10 over negative 1 makes a positive, so it's concave up. If I put 2 in, 2 minus 1 is negative, or is positive 1, 1 cubed is 1, negative 10 over 1 is negative, so it's concave down. That tells me there would be an inflection point at 1, but again, there's no point at 1. All right, so I didn't get any actual values here out of this. I do know about increasing and decreasing. So if I graph my horizontal asymptote at y equals 2, and I graph my vertical asymptote at x equals 1, I would just pick numbers near 1 to get some values. So if I just did a chart and maybe pick 0.5, 0, negative 1, negative 2, negative 3, that'd be going left. And if I picked 1.5, 2, 3, 4, 5 going right, that'd be some values to get for this graph. So y equals the function 2x minus 7 over x minus 1, parentheses 2x minus 7 divided by parentheses x minus 1. Type in all my numbers, 0.5, 0, negative 1, negative 2, negative 3, and 1.5, 2, 3, 4, 5. 0.5, 12, 0, 7, negative 1, 4.5, negative 2, 3.67, negative 3, 3.25, 1.5, negative 8, 2, negative 3, negative 0.5, 0.33, 0.75. So, I'm going to go at a 2 scale here on the y. So, 2, 4, 6, 8, 10, 12, 0, 7, 2, 4, 6, 7, negative 1, 2, 4.5. Oh, you know what? I'm going to move this down. Since I did a 2 scale, y equals 2 is right there. Negative 2, 3.67, so 2, 3.67 probably about here. 3.25, 2, 3, maybe 0.25. So it looks like it's kind of flattening out here and kind of going up there. And then 1.5, 2, 4, 6, 8. 2, negative 3, 2, 3. 3, negative 0.5. There's negative 1, negative 0.5 about here. 0.33 is about here. 0.75 is about here. And that one seems to be kind of going up like so. Notice verifying the results that we got. Vertical asymptote, horizontal asymptote, the graph seems to be staying within those boundaries. It's always increasing here with a break and then increasing there. So again, there's that break at 1, but increasing. It's concave up here, concave down there. All the concavity looks good. So that's what I'd be looking for that answer. And again, that's the whole quiz. So expect all the same types of problems. Prep yourself for the amount of time it's going to take you to do it.